Hello NuttX team. In this video, we shall talk about NuttX continuous integration or NuttX CI and how we automatically retry builds that have failed in NuttX CI. I'm very happy to declare with real solid evidence that our retry for NuttX CI, retrying the builds automatically, works perfectly okay. Yay! What does this mean for our NuttX developers? Automatically retrying builds that have failed in NuttX CI. Let me explain. We are now looking at the NuttX Build Monitor. This screen shows us all the recent errors and warnings for NuttX GitHub CI. Here is the URL. I will leave this URL in the video description. To understand more about the NuttX Build Monitor, click this link here. You will see a demo video that explains what this NuttX Build Monitor is all about. Right, let's look at the errors that have occurred in the last 12 hours. We filter by today's date, 20th of April, and look for errors. And we see that we have a couple of errors here. Now let's click on the first error here. Let's open a new tab. Let's find out what's this error about. We see here that this is trying to build an ESP32 target. It's trying to download something. We see that the download is Arctable3, but the download failed. It says that the zip file is corrupted, and therefore the build fails. Now, normally this kind of error will kill the entire build for extensor tree, and which will also terminate the entire CI build. However, with automatic CI rebuild, it will retry. We see that this is attempt 1 of 4. In a while, we see that it will restart the build. That's why we see attempt 2 of 4. We do not start it immediately. We have a random delay. This is what we call an exponential backoff. The first attempt, the first reattempt will wait 60 seconds. The next reattempt will wait 120 seconds, then 240 seconds. So it's an exponential backoff. But we also do a randomized backoff. Instead of strictly waiting 60 seconds, we will wait 44 seconds. And this is our second attempt. Second attempt, it sees that it downloads the same thing, and it works correctly, and it succeeds. Yay! And this is really what the CI Build Retry is about. If it fails due to a download error, it will no longer terminate the entire CI build. Instead, it will retry up to 4 times to re-download and rerun this build. In this case, we see that the second attempt was successful, and that's why it moved on to the next target and retried 4 times if they failed. This is one example of failure. We're not quite sure why this is happening to GitHub. It's not happening to GitHub specifically. It's also happening to other builds happening outside of GitHub, like NuttX Build Farm. But you can see that these errors happen in a cluster. They come across different configs. Like for example, we see Photon, we see NRF. And these are all happening at roughly the same time. So these failures tend to get clustered. It's very strange. We're not quite sure why, but the best we can do for now is to retry the builds. Because if we don't retry the builds, it will fail the entire CI build. And we will have to restart the build and waste our GitHub resources. We are limited by the number of GitHub runners that we are allowed to run GitHub jobs. if we restart our jobs too often due to these download failures, we will exceed our quota of GitHub runners, and this is bad. And also, this is quite bad for our developers. We don't want developers to see their jobs being terminated, not because of something they did wrong, but because of something that GitHub itself couldn't handle. With this CI build retry, we see that it will automatically retry the build, and it will succeed. Let's go into the next error to see what's wrong. Now notice that this is a different target. It's QEMU debug instead of fastboot. When we go in there, this is what we see. Now the pattern here looks a bit different. So this is the first attempt 104. It tries to download Arctable and it fails. According to our logic, it will retry the build after waiting a random number of seconds for the exponential backoff. It tries to build again. It tries to download the Arctable file again, and it fails. So that's 2 times that they tried to download the Arctable 3 build dependency and failed. Fortunately, we tried up to 4 times. That's why we go into a third attempt now. Notice that the exponential backoff is now 120 seconds, though we wait a randomized number between 1 and 120. The third attempt also failed. And our last and final attempt, thank goodness, it succeeded. This shows us why we need up to 4 build attempts. There are times when during our testing, we've seen that the downloads keep failing. Even though we're using a random exponential backoff, they don't seem to be 100% reliable. Downloads can still fail. And that is why we decided that we needed 4 attempts for our CI build retry. Through our own testing, we've seen that 4 attempts is the most that we will ever need for downloading a build dependency successfully to complete the build successfully. Now, it's also possible that we might need more than 4 attempts, but we'll monitor and to see whether this happens. So far, we've never seen any build attempt number 4 that fails. Maybe 4 is the maximum that we need. Let's head back to our NuttX build monitor. Our refresh has automatically updated the screen, so let's switch it back. We are filtering by today's date for errors. We see a similar error here, but it's a different target. This, I believe, is not ESP32. Let's take a look. This is coming from an ARM target, so it's no longer extensor, no longer ESP32. First attempt, download failed. Also for Arctable. Second attempt, download succeeded. You see that the pattern is quite different. The first time the first example we looked at, it succeeded after 2 attempts, then it succeeded after 4 attempts, and now it's back to 2 attempts. It's kind of unpredictable why this is happening. Let's move on to the next one. Now we see something different. This is a different target that's failing. Different target and also a different build dependency. This is happening for OpenAMP. OpenAMP is a library for asymmetric multiprocessing. It's used mostly for QEMU emulators. When our NuttX code needs to talk to an external host like QEMU to access I/O and networking, it will use OpenAMP. But this is not QEMU. This is happening for an NRF 5340. It's also an ARM architecture. Now we see here that it's trying to download OpenAMP /libmetal, and it failed. And a whole bunch of SSL errors, but really it means that the connection got terminated. That's why our script thinks that there is a SSL error. So moving on, let's look for the retry. It will go for a... Okay, there you go. Build attempt 2 of 4. Here's the second build attempt. And surprisingly, it also failed. So 2 builds have failed so far, all trying to download the same library, openamp/libmetal. Let's look for the next attempt. Let's do it the faster way, 3 or 4. There you go. This is the next attempt. And we see that, it succeeded. So this time, it took 3 attempts to download the dependency correctly and succeed. And eventually this entire CI job succeeded. Now you get the idea. What's this all about? We see similar errors. This could be quite similar to the ones you've seen earlier. CI Build Retry helps our NuttX developers. We see errors in downloading dependencies. These are downloads going to github.com, but for some reason these downloads fail, and it's beyond the control of our developer. What we are trying to do here is to help our NuttX developers by retrying the downloads and retrying the build, such that it will work correctly. This is a great improvement to our NuttX development process. Our NuttX developers no longer need to worry about their jobs getting terminated because of a failed download that's beyond their control. Now, next look at this. What happens to compile errors? Over here is an error that is due to a config problem. So it's a config problem or a compile error. Notice that it will also retry. We see here that this is a config problem. There's something to do with the LEDs and the UART, and it's failing. This is a config problem. When we see compile errors, it will look similar. What will happen to these errors? Well, our retry mechanism is very, very simplistic and very, very naive. It will not figure out what exactly failed in this build. As long as it fails, it will retry, which means that any config errors, any compile errors, it will also retry. If we move on, we see that this is build attempt 1 of 4. Right, okay, my mistake. Let's look for the original error. Let's say 2 or 4. Yeah. The original error is up here. Build 1 of 4. It failed because of this config error. Then we see that it waits a while for the random exponential backoff, and it heads on to the build attempt 2 of 4. Remember that this is a config error. For config errors and compile errors, no matter how many times we rebuild, it will fail. Well, our retry mechanism is quite naive. It doesn't know whether this is a config error or a compile error. It will just simply retry. And of course, as we all know, when we retry a build for a config error or a compile error, it will fail again. So we see that build attempt 2 of 4 fails. Build attempt 3 of 4 also fails. And finally, the build attempt 4 of 4 fails. That is why we limit our retries to 4. Imagine if we set our retries to 10. That means that for any kind of error, any compile error, any config error, it will retry 10 times, which will be quite a long wait for our developers. And this is quite bad also in terms of resource utilization. Our GitHub runners are limited. If we reattempt too many times, it will eat up our resources of GitHub runners. We exceed our quota for GitHub runners. And also remember that we do a exponential backoff. 10 attempts, with exponential backoff is a lot of time. We cannot afford that. That's why we had to limit it at 4. We had to limit it at the least possible number that will resolve 100%, if not 99%, of all download errors. Now, look what happens after our 4th attempt. If the 4th attempt fails, our script will kind of give up. Notice that it becomes build attempt 1 of 4, 2 of 4, 3 of 4. Then it goes to build attempt 1 of 1, which means that it will not do a retry. Here we see an error coming up here, but it will not retry this error. It will just simply skip ahead to the next target, and it will continue build attempt 1 of 1. Why do we do this? There are some errors that are like cascading. Simple error that appears on top will recur for all targets. If we attempt 4 builds for every one of these targets, it will stack up, it will add up, right? These cascading errors, we don't want them to affect our overall build time, to frustrate our developers and also to eat up all our GitHub runners. That's why when we hit 4 retries, we will kind of give up on retry. We will just simply build without the retry. And this will happen for all kinds of errors, whether it's a downloading error or whether it's a config error or whether it's a compile error. We will always do 4 attempts followed by and then switch back to max attempt 1. We will not do retry after that. We will see that from now on, everything is all build attempt 1 of 1, which means that we will not retry for any of these errors. And thank goodness we don't retry, because we can see lots of errors here. If we retry every single time, it will eat up a lot of time for our GitHub runners, and it will really frustrate our developers because this job will take a long time to complete. Here's one interesting consequence of our build attempt, and here's a useful tip. If you need to find out in this file what exactly went wrong, what exactly is a compile error. In the past, it was quite difficult. You need to scroll through the whole file to find out the compile error, right? Not anymore. We have a quick way. The quick way is to simply type 4 of 4, search for it. This will give you the exact error that failed. Remember that compile errors will always go through 4 builds and then it will fail, right? Therefore, if we just search for 4 of 4, it will return the compile error. Previously, there was no such way to find out what is a compile error. Now there's this cute trick that we can do. Of course, you don't have to type 4 of 4. You just type 4 off and it will also give you the result. This is a neat consequence of doing our CI build retry. Now we have a cute way to find out what exactly is the error that caused the build to fail. Just search for 4 off. Right, moving on. This is our build monitor. We have seen the errors for today. And as you can see, we just came up with another compile error here. Right. Anyway, but compile errors, we can't do much about it. We will have to bear with it. It will build 4 times, it will fail, but fortunately, it won't continue to do retries after this 4 fails. After these 4 builds have been exhausted. But as we can see here, we have evidence that download errors, yep, it works great. We see up to 4 downloads, retries working. The re-downloads were actually working. It caused the build to succeed, which is very helpful for our developers. And also helpful for NuttX CI team, because for us, we will look at this NuttX build monitor. Our CI team will see this build monitor, look at the status of jobs. If they see that they are failed due to download errors, we have to restart them. Well, fortunately for us, we see that all of these jobs are now succeeding perfectly because of the build retry. Build retry will auto fix any download errors. Typically, we'll see errors, in red because of download errors. And we can see from here that this thing is red, 18370, because it has compile errors. And we see that 18759 is failing also because of a compile error. So yeah, nothing we can do about these 2 except to fix the code. and we see that there are now 2 jobs that are running right now, and hopefully they will complete successfully also. We are monitoring the resource usage. The problem now is that with this new retry mechanism, any kind of error will also do a retry, compile errors, config errors. Therefore, we are mindful of the build times. We see here that this job completed in 3 hours 42 minutes, 3 hours 34 minutes, 3 hours 40 minutes. There's a chance that all these extra retries and also extra tries to re-download will eat up additional build time, which will take up more of our GitHub runners. The NuttX CI team, we are monitoring this number very closely. They seem quite okay so far. Typically, we see builds lasting 3.5 hours up to 3 hours 35 minutes, and that's before our CI Build Retry. Now with CI Build Retry, the number has gone up a bit. 3 hours 40 minutes, 3 hours 42 minutes, but we're monitoring this closely, and we think that right now it's manageable. Even with this retry mechanism, we are eating more GitHub runners, but it's worth it. Because the worst thing that can happen is that if we don't implement Build Retry, these download errors will kill the CI build, and we'll restart the CI build, which will take more GitHub runners anyway. So as the CI team, we are monitoring these numbers. We are supposed to keep our full-time GitHub runners below 25. Right now, past 24 hours, we are taking 10. This is quite okay, quite reasonable. And for those of us who have no access to ASF infra reports, just use the full-time GitHub runners, the live update, the stats here. Right, right now 11. And this number should be quite closely resemble this number here. Right. Now, what can we do about these compile errors? Now we can see that these compile errors will take up extra time to build. Our developers have to wait a bit longer, maybe 5 minutes longer, to see the build results. And compile errors will also consume GitHub runners. Therefore, we have to make sure that when we submit our PRs, we have to make sure that these PRs can compile successfully, are error-free as much as possible. The way to handle this is that we have a new system for doing building PRs in our own repos. The instructions are here. I will leave this link in the video description. The idea is that you can click on this thing called Manual NuttX CI, clone the repo, then just fill in your ID, your repo name, the branch you're trying to build, and just run. This will build your repo, your PR, inside your own repo, not inside the Apache NuttX repo. This means that any kind of resources that are incurred for this build, it will be charged to your account, not to our Apache NuttX account. And this will conserve the GitHub runners because the GitHub runners for Apache NuttX project are limited. By doing this, you will actually help to reduce the number of GitHub runners incurred to our project. So please use this way to build PRs in our own repos before submitting to NuttX, and we will be able to avoid these kind of errors and conserve GitHub runners for the entire project. Now, you might be wondering, how does this all work? How are we doing the CI Build Retry? Are we using a very complicated script to do that? Well, let me explain now. Surprisingly, the logic to do this is quite straightforward. We can find it inside our PR. This PR is called CI, Retry Build Upon Failure. Let's look into the code here. this is the documentation that we updated. Yes, we will now do an exponential backoff. Initially 60 seconds, then followed by 120 seconds, 240 seconds. And here is the changes to the script. There is an existing script called testbuild.sh. This script will build all of our NuttX targets in a GitHub CI run. All we did was to introduce a new function. Well, let me back up a bit. Previously, it will loop through all the targets in the target list file, the .dat file, like arm01.dat. Then it will call this doTest function to build one specific target, let's say sim:\nsh. We changed it. Instead of calling doTest, we just wrapped it into a retry test. Retry test is our new function that has the retry logic. And retry test is here. This is where we will loop through all 4 attempts. Max builds is initially set to 4. We will do tests here 4 times, right? And we will check if the build was successful. We will simply quit the loop. If it's not successful, we will do some cleanup and we will continue to the next build. This is the part, remember we said that if our builds have gone through 4 attempts and it still fails, whether it's a download error, compile error, or config error, if the 4 builds fail, the subsequent builds will not do a retry. That's why we set a max builds to 1 if we have exhausted all 4 builds, all 4 attempts in our retry. This is to prevent cascading errors from taking too much time to execute in our CI builds. And here is the exponential backoff. We will wait initially 60 seconds, then in the next loop we will multiply by 2, so it becomes 120 seconds. Then in the next loop it will multiply by 2 again, which becomes 240 seconds, right? And this matches up very well with the design that we originally planned, right? We plan to have 4 attempts. Each attempt will call doTest to build a single NuttX target. We will have a new function called retry test to do this 4 times. We did experiment with 6 times, but we found that 6 times are not necessary. These two times, we never had to use them. That's why we cut down the rebuild to 4 times. And also in our original plan, we had the exponential backoff. We will wait 60 seconds, followed by 120 seconds, followed by 240 seconds. It's actually 1 to 6, but then it's randomized. So it becomes 1 to 60, 1 to 240, 1 to 120, 1 to 240. And this is how we implemented the logic here. Now, there are 2 subtle bugs in here. I will explain in a while. There is one bug here in the cleanup of the corrupted downloads, right? And there is another bug here in the random exponential backoff. What do you think the bugs are? If you want to guess, pause the video now and figure out what is wrong with this code here for cleaning up the corrupted downloads and this code here for the exponential backoff. Right. Yeah. Now, the thing about the corrupted downloads, why are we doing this? The reason is that sometimes when we download files, it will stay there and our CI build script will not clean up the downloads. Now remember that this is happening, we are doing the rebuilds because sometimes our downloads get truncated, they get cut off, which leaves an incomplete file. Right? Our download failed, the downloaded file is incomplete. If we try to use that failed download, it will fail. Now, the problem with our build scripts is that it doesn't do a proper job of cleaning up. Subsequent builds will also try to reuse that failed download. Since the failed download is corrupted, the retry will also fail. It will try to reuse that failed downloads. It fails, right? And this happens 4 times. That is why we need to clean up any kind of failed downloads so that they don't get reused by subsequent builds, right? Like I mentioned, there is a bug in our cleaning up. There is a bug in exponential random backoff. I'm not going to explain now, but we'll come back to this in a while. Yeah, and this is our PR that has been merged to implement the CI Build Retry. As we can see, the CI Build Retry is really simplistic, really naive. It doesn't really care what kind of error it hits, whether it's a download error, compile error, config error. It will always retry up to 4 attempts. Why did we design this way? What is the rationale for making this so simple? Let's look at the PR here, and we will explain why we're doing this. First, the motivation. Why exactly are we doing all this? Are we really hitting a lot of download errors? Indeed, we are. We hit a record high usage of GitHub runners in January and February of 2026. During this period, we can see that here, January and February 2026, our usage of GitHub runners really spiked up. Normally, we need to stay below 25 GitHub runners, full-time GitHub runners, across any time, the entire year. This is the 25 is the limit that was imposed by ESF infrastructure team. We should not exceed 25. Otherwise, they will terminate our access to GitHub actions. Therefore, we should always stay below 25. But during this period of January, February 26, for unknown reasons, we were hitting very, very high peak usage. At the time, we couldn't figure out what was wrong, and we didn't have tools like the NuttX Build Monitor to see what was happening. What happened was that we did a retrospect analysis. We looked at the most expensive PR, then we went to the second most expensive, third most expensive. We also went to the apps PRs, and we came up with a whole spreadsheet of all the PRs. After this analysis, we discovered that the failure to download dependencies was really, really bad. There were times where it was trying to build dependencies for DTC device tree, Open AMP messaging, we saw this now, micro ADB debugger, MCU bootloader, Nimble Bluetooth, and they failed. As a result, the whole CI build got cancelled, got terminated, and we had to resubmit, restart the entire job, which accounts for the high peak usage in January and February. That was the number one reason for consuming so many GitHub runners, and also number one reason for frustrating our developers, because it's no fault of their own, but GitHub.com decided to fail our downloads and their jobs got terminated. The second reason for our high usage was the resubmitting of PR commits, which is kind of understandable. Because as you submit a PR, there will be changes requested, and therefore we resubmit a PR. But then, of course, there are some of us who will submit PRs not having tested properly whether they actually passed all the CI checks before submitting the PR, meaning that some of us will submit a PR that fails the build. This is the second most common reason for consuming so many GitHub runners. Therefore, this PR addresses the first issue. We are hitting too many download failures. They are killing our CI jobs. What can we do to prevent this from ever happening again, to prevent any peaks in usage in our GitHub runners. And as you remember, we should never hit too many GitHub runners. We should never exceed 25 for our GitHub runners. That's because if we do that too often, ASF infrastructure team will terminate our access to GitHub Actions CI. So therefore, we should never go there. Download failures are quite bad, as I mentioned. They will terminate the entire CI build and they will restart, and they will consume extra GitHub runners. Now, the other thing that gets worse also is that our CI jobs don't get terminated immediately. Our CI jobs will wait. Like for example, ARM01. If something happens inside ARM01, it will not be terminated immediately. What happens is that it will wait for ARM01 to complete, and then it will terminate the whole CI build. And we've seen examples from these that it gets terminated 2.5 hours into the CI build, meaning that we wasted 2.5 elapsed hours of our GitHub runners. But our GitHub runners are running in parallel. On average, we have 7.4 parallel processes, because there's not just ARM01 running, it's ARM01, ARM02, ARM03, and so on. On average, we have about 7.4 of these processes running in parallel. So when you multiply 2.5 by 7.4, that's wasting a lot of GitHub runners. And therefore, we must never make GitHub runners terminate our CI jobs. They are very, very costly. 2.5 times 7.4, that's a lot of GitHub runners. And that was the motivation for this PR. We want to retry the build for each CI target. Yes, we understand that our GitHub Actions has intermittent download failures, right? We will mitigate these effects. By retrying the build, we will be able to re-download it successfully, and the job will move on. It will not terminate a CI build simply because of one download failure. It might fail after 4 download failures. That's because our re-attempts is set to 4, but we haven't seen that yet, right? And of course, we really want to eliminate developer frustration. It's really bad for a developer to sit down there waiting so many hours for a job to complete, only to find out that it got terminated because of download failures. That shouldn't happen. We said that if the build fails after all 4 attempts, we will not be allowed to rebuild. This is to prevent cascading errors from overloading GitHub runners, consuming too much GitHub runners, and also wasting our developers' time. Now, why exactly are we doing this kind of simplistic solution that we will retry the build for any kind of failure? Well, we have 3 reasons here. I'll come to that in a while. Then we talk about this second point here. We discovered that during the peak period of January and February 2026, a lot of GitHub runners were wasted on PRs that were submitted without doing a compile check, meaning that the PRs had compile errors, and we submitted, they failed, therefore wasting our GitHub runners. Well, that's why we expect NuttX developers to build and test PRs in our own repos using this mechanism here, building PRs in our own repos, which means that we are now able to clone this repo and build any PRs in our own repo without charging it to the Apache NuttX project. Then it comes another problem. There are cases where PRs need to be submitted. Let's say our PR goes through a PR review, and it hits it gets reviewed, but it has a requirement that something needs to be changed. Our developer will need to resubmit the PR commit. But at this point in time, yes, we expect our developer to build and test PRs in their own repos using the method that we talked about. But because they submitted they resubmitted the PR, the build will automatically get triggered. And it may fail because when we resubmit the PR, it may contain some errors. What can we do about that? Well, we have a plan that we will be killing any CI jobs for PRs that have been switched to draft mode, which means that if we are submitting a PR and we need to change it due to some PR review comments, we will require developers to switch the PR to draft mode. Then we will have a background job that will monitor for any PRs in draft mode, and we will kill any CI jobs that are running for PRs that are in draft mode. That way, we will not incur any GitHub runners for PRs that fail while submitting PR commits. Right? We expect our developers to use this tool to build and test PRs in their own repos, make sure that it's okay. But at the same time, they have to switch their PRs to draft mode so that the PRs in draft mode will not incur any extra GitHub runners. And that's because we have this job to kill all the PR jobs. Just click on this link to see the video. This will explain more about our plan. In summary, before submitting any PR, we expect our developers to build and test the PR in their own repos before submitting to NuttX. Make sure that compile is okay. We don't want PRs to be submitted. They fail the CI checks because of compile error, which will waste our GitHub runners. Then, when we resubmit PR commits due to a comment due to a requirement of the PR review, we require NuttX developers to switch the PRs into draft mode. Then we will have a background process that will kill any CI jobs for PRs that we switch to draft mode. This will make sure that as our developers submit PR commits for a PR that's in draft mode, they will not incur any extra GitHub runners. And once everything has been tested okay, and the PR is ready for review, we will set the PR to ready for review mode. Yeah. And how we'll do this is that we'll make use of the NuttX Build Monitor to monitor some of these jobs. We will watch out for jobs that have been doing too many rebuilds. All right, moving on. We talk about our very simplistic solution for doing retry of CI builds. We'll retry the build for any kind of build failure. We talk about download failures, compile errors, config errors. We will always retry the build for any of these errors. It's kind of simplistic. Yes, why do we retry the build if it's a compile error or a config error? Logically, it doesn't make sense, but we are working within our constraints. The problem is that our CI team is really small and tiny. We have like a skeleton crew of 2 part-time volunteers working on everything in NuttX CI. So this includes the day-to-day monitoring of all our CI jobs. We cannot afford to roll out and maintain complex CI solutions. What's an example of a complex CI solution? Well, in theory, we could capture the output of a CI build and do some analysis to figure out whether this is a compile error or a download error or a config error, which is actually quite hard to do because we need to do some kind of regular expression, we need to do some kind of parsing, maybe even some kind of AI to figure out why it failed. Our error messages, unfortunately, are quite poorly structured. We have no idea of figuring out what kind of error this is. We can't simply look at the text to see whether it's a download or compile or config error. In fact, the errors that we see today, we can't even tell what kind of errors it is. It could be a warning, it could be the error. That's why we're picking up these kind of strange messages, because we couldn't decide whether these are errors or warnings or something that we can ignore. So because of this constraint, we are not able to build a complex CI solution and maintain it, right? And it's because we don't have enough people to do this. The next thing is that we are mission critical. It must run 24/7. During peak periods, we saw earlier, like January and February, and also during release windows for NuttX. NuttX CI must never be allowed to fail. If we implement a complex CI logic, there is a chance that it will fail. Maybe our CI logic thinks that it's a download error, but really it's a compile error or config error. Well, these kind of logic errors are disastrous. We cannot afford to have NuttX CI fail during peak periods and during NuttX release windows. That's why we implemented a really simple mechanism here that will never fail. Also, keep in mind that we are dealing with very complex CI scripts. A lot of CI scripts we have inherited, they are really complex. We don't really want to go in there and patch individual CI scripts. And different CI scripts do things differently. For example, ESP32 downloads, they do it very differently from the rest of NuttX. We don't want to go into each of these scripts and figure out, how they download and then retry these downloads if they fail. That's why we went on a alternative, simpler solution. We just implement a new wrapper function that will call an existing function to do the retry. We do not touch any of the legacy CI scripts. We keep them 100% intact, but yet we introduce a high-level retry function, a wrapper function that will retry the existing builds. That way, we don't have to test too many changes, and we don't have to worry about breaking any legacy CI scripts. Then we talk about the compile error and config errors. Moving ahead, we really hope to have all NuttX developers to use this way to build and test PRs in our own repos before submitting to NuttX. There's also a chance that compile errors and config errors might cause cascading build failures, which is why we implemented the maximum retries of 1 if we hit any errors. Which means that if we try 4 times and we fail, we will not be allowed to retry anymore for other subsequent builds. So this solution is really simple. But CI builds will now be slightly slower. Remember that we are not able to distinguish compile errors and config errors from download errors. CI builds will be slightly slower, meaning our NuttX developers will have to wait a bit longer for the CI build to complete, because compile errors, config errors, they will also undergo 4 build attempts. We did a measurement. For a typical job, it will take roughly 5.6 minutes slower, which is quite manageable. But then again, if our NuttX developers, if we do not wish to wait for these 4 retries of compile errors and config errors, please, we really need to build and test PRs in our own repos before submitting to NuttX, which means that they will not have compile errors and config errors, and therefore we don't have to wait the extra 5.6 minutes for it to undergo retries. Now, this 5.6 minutes is for a typical job. It might get slower. There are some CI targets that will take longer to run. For example, the CI test. CI tests are the ones that will run in QEMU inside GitHub Actions to verify the execution logic of our code. These will take longer. It should be longer than 5.6 minutes. So therefore, if we build and test PRs in our own repos, then it means that our CI test will be successful and we will not be submitted to a longer delay if the CI test fails, because the CI test won't fail, right? Why did we retry 3 times. We tested the logic over the past 4 weeks across 50 builds in NuttX production. We noticed that we hit a maximum of 4 attempts, and that's why we decided on 4. We actually implemented 6, but we never had to do a 5th or a 6th attempt. After 4 attempts, everything was okay, and that's why we stuck with the 4 attempts. But just kind of note that in general, it's very hard to reproduce a download failure. It happens in GitHub for sometimes, and it tends to be clustered. We're not sure when, we're not sure why, but it just happens. So over the past 4 weeks, even across 50 builds, we only encountered about 6 instances of download failures. And of all of these 6 instances, we hit a maximum of 4 attempts. We never had to do 5 or 6 attempts. That's why we stuck to 3 retries, 4 attempts. And this number is quite small. We only encountered 6 download errors over the past 4 weeks across 50 builds. It's probably a very small sample size, but we will continue monitoring. We will see if any download failures will still happen, exceeding the 4 attempts. And we have some test cases here to simulate compile errors and config errors. We make sure that they do not get retried after exceeding the 4 attempts. Some of you might wonder, why are we handling this download failure? Why do we retry at all? Shouldn't we escalate to GitHub and let them resolve it? The reason is this. We run outside GitHub Actions a NuttX build farm. This is a build farm that we run NuttX build jobs continuously, 24/7. And it's running outside of GitHub. It runs on a home PC, a very powerful home server. And we see the same download failures, which means that it's not a problem specific to GitHub Actions. It could happen to anything. And that's why we should always assume that GitHub, that dependency downloads are not perfect. We should always retry, right? Therefore, it makes no sense to escalate to GitHub. It's not a problem specific to GitHub Actions. It's also happening to our home PC. But it's a problem with GitHub.com. It will try to download from GitHub.com and it fails. Why? We're not sure. When this happens, we check the GitHub status, the GitHub incident logs. It's not reported. There's nothing wrong with GitHub at that point in time. So it doesn't seem to be a problem with GitHub Actions because it's happening outside of GitHub Actions. But for some reason, we couldn't download some of these build dependencies hosted at github.com. Maybe it's a CDN problem. Maybe it's a Microsoft Azure problem. But but we can't afford to wait. Meanwhile, we have to go ahead and we have to do this our way. And resolve it. We cannot afford, for somebody at GitHub to figure out what is wrong with github.com and why is it blocking our downloads, even from within GitHub. And these are 2 instances that download from github.com failed, even from a NuttX build farm running on our own home PC. Now, there is one thing in common though. NuttX CI always runs in a Docker container. We use the same Docker container, the NuttX Docker image, inside GitHub Actions and also in NuttX build farm. There is a slight possibility that our Docker image isn't configured correctly for networking. Maybe under some specific circumstances, our configuration for our Docker image, it fails. Maybe due to too much load or, due to some other strange circumstances. It's possible, but too bad. It's very unfortunate. We don't have anybody in our team to troubleshoot Docker networking. This Docker image was a legacy project that was handed over to us. And frankly, we don't want to touch it too much. It might break. And if somebody is familiar with Docker networking, might want to take a look. It might be possible that there is a bug in our Docker networking inside the NuttX Docker image. We also thought about this. We are using curl commands to download build scripts, to download build dependencies in our build scripts. Why not fix them? We did a search. We have 73 curl commands in our build scripts. We can see the list here. That's a lot of curl commands to change, and you can see that the commands, the options are all different. It becomes very frustrating, and it becomes it becomes a chore really to go through each one of these and fix all 73 of these curl commands to do retry. And then once we do that, we will need to test all 73 curl commands. And some of these curl commands may not even be used by CI scripts, that we have to go in and test all the targets that will make use of these curl commands. This is a bit too overwhelming for our CI team. We are very small. We've got 2 part-time people. We are not able to fix and test all 73 curl commands. But yeah, I mean, ideally that could be the best way to do it. If we had a great big NuttX CI team, we could do that. But right now, no, sorry. For your info, curl also supports exponential backoff, but then it's not randomized, right? Then there's another issue. Curl commands. Yes, we see the curl commands for these build scripts, but we don't see any of these curl commands for the ESP32 downloads. ESP32, unfortunately, uses its own way of downloading files. Well, we are not able to see how they download files. The curl command is not visible to us. And we really don't wish to go inside ESP32 framework and patch the way it downloads files. Right? And in fact, we don't even want to touch all these scripts here because these are legacy scripts. So we have a problem. Yes, we can fix all 73 curl commands, but there are some that are untouchable. We have download commands running inside the ESP32 framework that we do not have access to, and we could not change the download options to do a re-download and to do exponential backoff. That's out of the question, right? And that's why we still prefer to stick with the current way of doing a CI build retry. Okay, we shall move on. Remember we said earlier that there is an issue with the backoff. Let me refresh your memory about the code here. If you look at the code here, this is the logic that we use for the backoff. Every time through the loop, we multiply the backoff delay by 2. Initially, the backoff is 60, multiplied by 2 becomes 120, multiplied by 2 becomes 240. And then we do a randomized delay between 1 and the backup number. What is the problem with this? There is a very subtle bug. As Nathan has pointed out, yes, there is a bug. The bug is this. We do not impose a minimum backoff, meaning that there is a chance that the second delay might be shorter than the first. It's a random delay, right? So the first random delay is between 1 to 60 seconds. The second random delay is between 1 to 120 seconds. So let's say the first delay is 60. The second delay is random. It could turn out to be 59 or something less. That's why this logic is not quite technically exponential backoff. We may encounter cases where the second retry, the second delay is actually less than the first delay. So technically it's not really strictly a exponential backoff, which is why Nathan has suggested that we do a initial backoff, we do a minimum backoff, and we make sure that the backoff delay will always increase, it will never decrease. Technically, yes, this implementation is correct. My implementation is incorrect, it's wrong. However, let's stick with our current implementation for now. The reason is that we have tested this code for 4 weeks. It seems to be okay for now. Let's see how it works. Maybe this is good enough. Also, when we impose a minimum backoff, it also means that compile errors will take longer to complete. And therefore, it will frustrate our developers a bit more. Even though technically our developers need to use the new tool to build and test PRs in their own repos before submitting. We had an idea here. The idea is that what if we created our own repo for caching dependencies? Will it work? Now, the problem is this. It requires maintenance. We will have dependencies, yes, in our own repo, but we need to cache them. There may be a new version of, let's say, ESP32 framework, ESP32 runtime. Somebody needs to go in and refresh the dependencies in this repo. And it's not a fully automated job. The dependencies caching may fail. Therefore, we need somebody to monitor this and make sure that it works. ESP32 downloads, I mentioned, are a bit tricky. We do not see the curl command to download ESP32 downloads. It's hidden somewhere within the framework, and it does its own way of doing ESP32 downloads. I will talk a bit about that in a while. And ESP32 downloads might need more attention, might need some manual intervention to upgrade. Because when there's a new version of ESP32 framework, we have to make sure that it rolls out smoothly and successfully to all our NuttX builds. Then the other problem with caching dependencies at CI depths is that the download failures are not for external dependencies. The download failures are coming from GitHub.com. GitHub.com has trouble serving us the build dependencies that it hosts. GitHub Actions cannot download the build dependencies from GitHub.com, even though it's the same entity. So if you're talking about external build third parties hosting our build dependencies, yes, I understand. We should try to cache them. But it's now GitHub Actions failing to download something from GitHub.com. It's very strange. Why is this happening? Maybe it's because we are spamming GitHub.com too much. Remember that we are running parallel jobs. When we start a CI build, it will do ARM01, ARM02, ARM03, and so on. There could be 10 jobs running in parallel. All of them will try to download build dependencies at the same time. This will cause spamming of GitHub.com. Then GitHub.com will block our downloads because it thinks that we are spam. And that's why we did the random exponential backoff. But this is my theory about why GitHub.com is blocking our downloads. We're not sure, but yeah, so it's a problem. If we have cache dependencies at NuttX CI depths running in GitHub, but then our download failures are at GitHub.com, it's not going to help. Yeah. And for downloads for external third parties, yes, we actually did a fix here. We had a problem with the libyuv library hosted at chromium.googlesource.com. It suddenly decided to block us one fine day. That's why we moved the library into our NuttX mirror repo. Won't we have the problem about auto-refreshing the dependencies? Well, this library hasn't been updated since 2021. That's why we don't have to worry about refreshing. Yeah. ESP32 downloads, yes, we have a problem here. It's a bit harder, it's a bit obscure. I'll talk about it in a while. This is a suggestion about doing a short 10 seconds delay, random delay before each download starts. It's kind of strange. So, as I mentioned, we did this testing for 4 months straight. We only encountered like 6 instances of these download errors. Out of the majority of downloads, they are fine. But sometimes we will just see a lot of download errors. Like for example, over here, we see a storm of download errors. It seems to be happening at certain times of the day of the year. We're not sure why. Therefore, it's not really helpful to introduce a short delay before every single download. There is a 90% chance that the download will succeed. So there's no reason to do a 10-second delay. But in really, really strange cases, really, really weird timings, GitHub.com will suddenly have a storm of errors and it will refuse to have any downloads. And this will happen within GitHub Actions and even outside GitHub Actions, as we are seeing in our NuttX build farm. That's why I'm not quite keen to do a short wait before each download. 90% of the time, it will succeed. It's just within this 10% of this unpredictable stormy periods that GitHub.com suddenly refuses to work and refuses to serve any downloads. And that's where we need to worry about this weird period of 10%. And that's why the retry will help. So I don't think it's fair to penalize every single download with a short random delay, because most of the time it will succeed 90% of the time. Now, but moving ahead, we have lots of issues about doing any kind of meaningful updates to NuttX CI. Build dependency caching, for example. And also going into the build scripts and changing the curl commands so that they do exponential backoff and retries and all that. The problem is this: we don't have a proper CI team in place to handle all of this extra work. Why are we not able to roll out any significant changes to NuttX CI to make it really good, to fix all the issues that we have? The problem is with our NuttX CI team. We don't really have a CI lead to take care of all these projects, to take care of any CI projects, the implementation, the monitoring after rollout, and the maintenance. Today we have 2 part-time volunteers, and that's all we have in our NuttX CI team. We don't have a lead who will take care of everything in CI. And this is not an isolated project. Suppose we have identified a CI lead to front all these NuttX CI enhancements. The CI lead does not work in isolation. The CI lead will need to depend on expertise from other architectures. For example, we need to have owners for every single architecture, like ARM32. There'll be an ARM32 owner who will advise on everything related to ARM32 builds. ARM64 owner for ARM64 builds, RISC-V owner, and even an extensor owner. Remember we talked about ESP32 downloads, and it's a bit obscure and we couldn't figure out how it really works. That's why our CI will need to consult the extensor owner to understand how the downloads work. How do we tweak it so that it supports retry? This needs very specialized knowledge that the CI lead is not able to handle on its own. This thing is not something that CI lead could all understand. The CI lead will need to consult an expert like the extensor owner to understand some of these things work, like downloading of ESP32 dependencies. Our suggestion also is that the ARM32 owner is actually covering quite a lot of boards in NuttX. We need to have a delegation, right? What if we could have a representative for every single type of board? STM32 boards, RP2040 boards, and so on. There will be a representative to cover these kinds of boards. If there's a CI lead has a question about ARM32 downloads, the ARM32 owner may have to consult these representatives to figure out how these things work. For example, RP2040, Again, it has built dependencies. They are quite different from the rest of the project. The ARM32 owner may have to talk to the representative for RP2040 to understand how downloads work for RP2040 builds and figure out if we can do the download retry correctly. Which means that we cannot roll out any kind of any kind of proper fix to the download problem unless we have this kind of situation, this kind of structure. We need a CI lead, we need owners for every architecture, and we need representatives, if possible, for different kind of boards. It will be quite difficult to identify all the owners and all the representatives, but it'll be good to have some. For example, today maybe we'll have an ARM32 owner, so that upgrades can happen incrementally. We will roll out CI upgrades to ARM32, and maybe someday we roll it out to ARM64 when we identify the ARM64 owner. This is the kind of structure that we need, and we don't have this structure right now. That's why it's holding us back from doing any kind of impactful, meaningful upgrades to our NuttX CI. We have lots of ideas for doing new things in NuttX CI, like for example, doing a memory utilization chart for NuttX CI. But that requires time and effort to add the future to NuttX CI. We need time to test it. We need time to document it. Then after rollout, we need time to monitor it and also to maintain it. That's a lot of work for 2 part-time volunteers to handle right now. And the volunteers are, both of us are busy looking after day-to-day operations like this. We have to make sure that all builds are running. We have to make sure that all our builds are in green, nothing is in red, and they all complete within the assigned time. We have to make sure that we are not exhausting too many resources of our GitHub runners. Therefore, it's quite tough for us to roll out a lot of interesting updates. There are lots of interesting things that we could do, like CI build dependency caching, but unfortunately, we do not have the CI lead. And unfortunately, I cannot be the CI lead because I suffer from hypertension. We need ARC owners, only architecture owners to advise the CI lead. We need board representatives. We have any problems with ESP32 downloads, we can ask the extensor owner. We have curl commands to fix, 73 curl commands. That's a lot of commands to fix. If we have ARC owners and we have board reps to test all 73 upgraded curl commands, that will be awesome. We also have concerns about rolling out new tools. Remember that our NuttX developers are on Mac OS, WSL, Ubuntu, FreeBSD, and all that. We need these tools to support all these platforms. So sometimes some of these tools are non-trivial to roll out. They require lots of testing and coordination. And also, this is super, super important. We need to worry about having an operations person. Right now, we have 2 part-time volunteers. We will stare at this screen once a day, or maybe a few times a day. So the thing is this sustainable? Can we really have our volunteers staring at this thing to make sure that all our builds are running okay? Making sure that our failed downloads are retrying correctly and they're actually working correctly. It becomes a burden. And we are thinking we really need an operations person, preferably a paid operations person. This person will be paid to stare at this screen every day to figure out if our NuttX builds are running okay, whether we need to do any tweaks to our downloads, our retry downloads, to make sure that they work okay, and to make sure that all our builds are completing within reasonable times. And once we roll out things like caching or build dependencies, we need to worry about them being cached correctly. And we need to worry about them being updated. Suppose someday somebody discovers a security vulnerability in one of our build dependencies. Well, that dependency needs to be updated in a timely way. That's why we need an operations person to go in to monitor these security advisories and to patch these these build dependencies in our cache, so that our builds in NuttX will not have these security errors, right? Will we have this paid person to monitor our NuttX CI? Well, this will affect our redesign. If this person is around, maybe we will not have implemented CI Build Retry in the simplest way possible. We did this the simplest way possible because we're looking at a implementation that does zero maintenance, zero monitoring. It's something that is just do it once and forget forever, hopefully. Once we have a operations person, then maybe we have more leeway, we have more flexibility in designing more sophisticated solutions. Remember, we talked about a CI solution that intelligently discovers why this build failed. Is it a download error, or a build error, a compile error, or a config error? Well, this kind of intelligent processing, intelligent parsing, will need an operations person to monitor. Once we have this person around, it will be easier to implement, and it will be more successful. And and we will waste less time of developers, less time for our GitHub runners. Now, we have another potential solution for fixing these download problems. The suggestion is this: why don't we include these downloaded files inside the Docker image? Yes, it's possible, meaning that we bundle the build downloads inside our Docker image, so we don't have to download at build time. However, again, it's a operational overhead. It means that somebody needs to maintain the Docker file to put in the latest updates for these build dependencies. Suppose someday we need to upgrade some of the build dependencies because there's a new version, or because there's a security vulnerability, and we need to update these build dependencies. Well, that means we need to rebuild the Docker file. And unfortunately, rebuilding a Docker file is an operational issue that we try not to touch because it's a lot of work and it's a lot of testing. It's not as simple as just putting in a fix into a Docker file and just rolling out to production. It doesn't work that way. We have to test it. So our Docker files, we tend not to make any changes to it because it's really a chore to maintain the Docker file. It's a Docker image that's got lots and lots and lots of dependencies in there. We really don't want to break anything inside there. Docker file sounds like a great solution, yes, but we need effort, we need people to be able to maintain this. With our current skeleton crew of 2 part-timers, I don't think so. If we are able to find an operations person, paid preferably, to do this work on behalf, going into the Docker file to maintain these dependencies, rebuilding the Docker file, retesting the Docker file every time there are changes, yes, that will be a very, very nice solution. Unfortunately, not today. Sorry. Remember that we spoke about this script here, and I talked about an error here. So we saw that this code is technically not correct because the exponential backoff for the second retry could be less than the first retry. There is a fix for doing a minimum backoff, but we'll hang on to that for now because this is the code we actually tested for the past 4 weeks. There is another subtle error here. The problem with this code is that when our build scripts download build dependencies and the download gets cut off, gets cancelled by github.com, we will be left with a partial download that's corrupted. It will not be able to be used for the build. But the problem is that this corrupted download, it gets reused by subsequent attempts. Meaning that when we do a second attempt to build, it will reuse the same corrupted download. The build scripts are kind of naive, really too naive. If it sees a .zip file, it will simply assume that a .zip file is perfect, and it will just reuse the .zip file. Yeah, very naive, right? But it's causing problems for us. Therefore, we have to cancel and clean up any corrupted downloads if we see them before we do the next attempt. And the lesson learned is this: if we are writing scripts to do any kind of downloading, please always check the result of the download. If the download has failed, never keep any partial files, any zip files lying around. Please clean up properly and delete any of these errors, so that we don't have to do this funny job. But anyway, today we are stuck with that. We have to worry about cleaning up any partially downloaded, corrupted downloads. And these are the commands that we use. Git clean fd. But there is a bug here. The bug is this. The problem with git clean fd is that it will not remove some types of corrupted downloads. Some of them it works, some of them it doesn't. So we simulate this error by doing this. Let's say we configure the sh. We configure for our target netnsh for QEMU. It will download some dependency, and we press Ctrl+C to start the build. So yes, there will be a zip file, and it could be corrupted. Following the steps we saw earlier on, we could do a git clean -fd, but problem is that the file stays there. Arctable is still there. The correct command should be git clean -xfdq. If we do this, we find that the corrupted download is deleted correctly. Yeah, and in fact, if we look at the test build file, there is a dist clean step, and it uses these two commands: git clean -xfdq. That's why we decided to change the script so that we will not use git clean fd. We will now use git clean -xqfd. This will really clean up any corrupted downloads, and that's why today we have evidence that this works. Before I wrap up the video, let's talk a bit about ESP32 downloads. ESP32 downloads, I mentioned, are a bit special. They do not appear as curl commands in our build files. They are hidden somewhere within the framework. Unfortunately, we need to consult somebody in the ESP32 team, some extensor expert, to figure out how it works. But within our NuttX CI team, we are trying to get a rough feel to understand how it works, and this is an interesting clue that we have. So based on this PR here, we found something interesting. We see that there's something called a NXTMP DRL. It actually contains a cache version of the how ESP how third-party repo. And it's not within the NuttX tree or the apps tree. It's within the parent folder. So it's NuttX NuttX temp DR and ESP how third party. This is a problem. This means that internally the NuttX build for ESP32 is downloading some build dependencies. And actually it's a repo. And I have seen cases where the download of these repos fail because GitHub.com is not 100% reliable. You should not assume that it's fully reliable. What happens if this repo fails to download? Well, then there's a high chance that our build will fail. And remember that we're doing a retry of CI builds, right? We will retry if anything fails. If this repo fails to download from GitHub.com, well, it will retry. But the retry will not help because it's going into a different folder. Right now we are doing cleanup, yes, but our cleanup is happening only within the NuttX folder and the apps folder. It does not clean up for this folder, NuttX temp directory in the parent folder, which means that yes, we might need to delete this folder while retrying the CI builds, because there is a chance that the Git clone of this repo fails. It contains corrupted downloads, And if we don't delete this folder, it will retry the build using this corrupted folder. That's why, we need to monitor this. We need to see what kind of retry problems we're having with ESP32 builds. If necessary, we will need to delete everything in this folder before we do any retries. So this might be a upcoming enhancement to our retry of CI builds. We are finally at the end of this super long video. What we talked about today is our retry of failed builds in NuttX CI. And this will help to fix any kind of download errors that will happen in our builds. So far it's working. We see very good results, which means that we will no longer waste GitHub runners on jobs that fail because of failed downloads. And our NuttX developers will be happier now that their jobs will not fail because of failed downloads. How we fix it is that the build will simply retry, and the retry will do a re-download up to 4 attempts, and we've seen so far that it works. The re-download works, the job continues, and everything succeeds. Everything becomes green. We also talk about some of the reasons why we came up with this very simplistic solution. We have lots of constraints. We have a very small team. We're not able to do everything that we wanted. We are not able to do a proper analysis of every single build failure, to understand whether there is a download error or a compile error or a config error. We did the simplest solution possible due to our constraints, and it seems to be working so far. Yeah. And again, we wish to remind all our NuttX developers, please use this method to build and test PRs in our own repos before submitting to NuttX. That's because our new retry mechanism, our new retry logic, will also retry builds for any kind of config errors or compile errors. Therefore, it's good to use this way to build and test PRs in our own repos to make sure they are free of config errors, compile errors, before we resubmit them. Because if we submit a PR that's got compile errors or config errors, it will take longer to come back with the error due to the retry mechanism. Yep, and that's it for today's video. So I hope that everybody gets a lot happier. We will be able to finish builds faster because it will handle retries correctly, and our builds will no longer be cancelled. And also our ASM infrastructure team will be happier because we are using fewer GitHub runners, because they're not wasted on restarting jobs. And of course, our NuttX CI team, we will be really happy because we will see more jobs succeeding, and we don't really have to go in there, click in, and restart any failed jobs due to failed downloads. Thank you so much for listening to me, watching this video. If you're looking for the links to these pages, I will keep them in the video description, and I will make a video if there are any updates. Thank you so much. Bye.